Hello and welcome back to the course on artificial intelligence. I hope you're enjoying the course so far, and today we're talking about action selection policies. All right, let's dive straight into it. Previously, we talked about adding a neural network to our simple Q learning, and so far we're getting quite into deep Q learning. We've talked about the learning part quite a bit, including adding some elements to it, and today we're talking about this part. We're talking about the acting. So let's have a look. So here we've got what we discussed about the acting, that once you input the values, the parameters or the vector describing the state the agent is currently in that environment, then that is after all the learning is done, or even before the learning is done, basically we get all the Q values. So we're not interested in the learning right now, we're interested in the acting. So once we have these Q values, how do we understand which one we need to use? Well, if you think about it, Q values are simply, these are the predictions for the Q values. So as we did in the simple Q learning algorithm, what did we do? We just selected the one with the highest Q value. Once we have the one with the highest Q value, we just take that action because it just brings us the highest Q value, and that we know that Q value is calculated as the immediate reward that we expect to receive plus the decay factor times the value of the next state, and it's a recursive calculation. So why not? Why wouldn't you take the best Q value, and that's kind of the end of it. But as you can see here, it's not as simple. Here we're using a softmax function, and this is where we're going to talk about action selection policies. So here, in reality, we don't have to have just a softmax function. We can have different action selection policies. For example, we've got epsilon greedy, epsilon soft, and we've got the softmax. And those are kind of like the most commonly used action selection policies. Of course, there are others. For instance, the most basic one is, here's a very simple action selection policy. Just select the best, the one with the highest Q value. But why doesn't that action policy fly? And why do we have different types of action selection policies? Well, it all boils down to exploration versus exploitation. And that is the core of reinforcement learning, because we've already talked about this a little bit, that your agent, when it's operating in an environment, it might predict certain Q values, which might be good, and it might not turn out great. It might turn out that those Q values are bad, and it'll be forced to explore. So if we, for instance, in this case, predict that Q2 is the best one, and then it takes Q2, takes action 2, and so from here it takes action 2, and then it gets a very negative reward. Then the environment is forcing the agent to go and explore, because now it's going to learn that, oh, actually, I thought Q2 is going to be very good, but it turned out very bad. So the result turned out very bad. So the network is going to update itself. So next time he's in this state, he might still choose Q2 if it was, if it was very, very favorable. So you might think that's like, he might need a couple of penalties, punishments in order to learn that Q2 is a bad action. But maybe he'll already soon learn that, okay, I'm going to take a different action. I'm going to take this action because now it has the best Q value. So sometimes the environment forces the agent to take to explore different actions. But sometimes the agent might find itself stuck in a local maximum. It might find that it found, like through its initial exploration, it found that, oh, this is a pretty cool action. Like, I'm going to go right here. And that's a pretty cool action. But the problem is that it thinks it's the best action simply because it hasn't explored. It's explored going up, it's explored going left, it's explored going right, but it hasn't explored going down from that specific state that it's in. And now that it's kind of like biased towards this action, it thinks it's a good action, it's going to keep taking this action, it's going to keep getting a good reward. But what if this action would have been even better? If this action would have been so much better that if it knew about this action, it would actually switch to this action. But because it got stuck in a local maximum and it's getting these good rewards, it's just going to be reinforced. It's just going to keep reinforcing itself or the environment's going to reinforce it that this is a good action to take, keep doing that. But the reality is that there's this other action that it hasn't found yet or hasn't even explored that would have been much better. And so what we want to do is we want to come up with an action selection policy that allows our agent not to get stuck in a local maximum. Yes, it's important to keep doing the good actions. That's the exploitation part. We want to exploit what we've found, but at the same time, we still want to explore. We never want to stop exploring. It's like in life, you never want to stop learning. You stop learning, you die. There's a saying like that when you're not growing, you're dying, or something like that. So you want to keep learning, and your agent wants to keep learning, and that's where these action selection policies come in. So we've got 3 listed here. So the first one is epsilon greedy. It's a very simple one. It sounds pretty complex in the sense that like it's got a cool name, and usually things with such cool names are complex. It's not. It's actually not. So basically, what it does is it will select the one with the best Q value. And epsilon greedy, you might hear it in other places. It's just like a selection policy. So in this case, we're using it to select our out of our Q values out of our action. So you'll select the one with the highest Q value all the time, except for epsilon % of the time. So for instance, if you set epsilon to 10%, then you're going to, or 0.1, then 10% of the time, the action is going to be selected at random. So 90% of the time, you're still going to be selecting the best action based on the highest Q value, but 10% of the time is going to be selecting a random action. Uniformly, just going to be absolutely randomly taking an action. Or if you set epsilon to 0.5 or 0.05, that means that 95% of the time, the agent is going to be taking the action with the highest Q value, but 5% of the time, it's still going to be selecting a random action. So it's going to be going out there and exploring. So epsilon soft is very similar. Oh, by the way, that's kind of like why it's called epsilon greedy, because you're greedily selecting the action, the good action, except for that little epsilon % of the time. So the lower the epsilon, the more greedily you're selecting that kind of the action that is the optimal action, and the less you're leaving, less chances you're leaving for exploration. Epsilon soft is the opposite. So basically, you're selecting at random, you're selecting 1 minus epsilon % of the time. So if your epsilon is like 0.1, so 10%, then only 10% of the time you're taking this action, and 90% of the time you're selecting a random action. So very, very simple, just inverted algorithms. And softmax is kind of like the next step from, or it's a more advanced version, I would say, of the epsilon greedy algorithm. Although they both have merit and they both have place, we're going to be using softmax in our coding, in our practical side of things. So that's why we're going to talk in a bit more detail about softmax. So let's have a look. So let's move on to softmax. Hopefully it's pretty clear about epsilon greedy. It's a pretty straightforward algorithm. Select this one most of the time, except for sometimes go and explore. And now we also see why it's important to do that exploration, so that we don't end up in local maximums in our optimization process. So now we're going to talk a bit more about softmax. There's a tutorial on softmax at the end of the course. I think it's in Annex number 2, where we talk about the concept behind softmax. I'm just going to refresh a little bit here. So there we're talking about convolutional neural networks. And by the way, we aren't going to be covering we're not covering convolutional neural networks in this section of the course. In this section, we're still using a vector. But in the next section of the course, when we're creating an AI to play Doom, we are going to be using convolutional neural networks. So it could be beneficial for you to look at convolutional neural networks and then take the softmax function, or you can learn a bit more about softmax after you take the convolutional neural networks annex of the course later on. But here's a quick refresher. So here we've got a convolutional neural network which decides whether it's a dog or a cat. So here we've got the voting process between these neurons, and this one says that it's got the features, the fluffy ears, the pointed face type of thing, and the kind of like the features, the types of eyes, the way the eyes look, all these features that belong to a dog. So it's a 95% chance that it's a dog and a 5% chance that it's a cat. But the question is, how did we get, and in that tutorial, we're talking about how did we get these values to add up to 1? Well, whatever the convolutional, our whole neural network, so the convolutional neural network plus the fully connected layers, whatever it's spat out, whatever the values it spat out, we applied a softmax function over here. And this is where we introduced the formula for the softmax function. This is what it looks like. And then we got these values. And so basically that's a quick refresher. This is the formula for the softmax. What it does is it takes however many outputs you have, doesn't matter, it will take them and it will squash them all into values between 0 and 1, regardless of how big they are. Just by looking at this formula, you can see that there's a total sum at the bottom, so these values are going to be between 0 and 1, and also all these values are going to add up to 1 always. And so that's very beneficial for us because when we're using the softmax function, what happens is we get these Q values. We select this best Q value, but in reality, what happens is these Q values that we get, they're actual numbers, right? So there's some kind of numbers. They don't have to add up to 1. They don't have to be between 0 and 1. Just some numbers. But when we apply softmax, we don't just select the best one. We actually get numbers like that. So we get numbers in the range between 0 and 1. And that also add up to 1. And so what other thing do we know that adds up to 1? Well, probabilities. We know that probabilities always have to add up to 1. So that is why we can say here we've got Q values, but here all of a sudden we've got we've got probabilities. So we can say that the likelihood of this being the best action is 90%. This being the best action is 5%, 2%, 3%, because we know the higher your Q value, the better the action. And so if we squash them to 0 to 1, then these become probabilities and we can deal with them as such. And therefore, now is when the action is selected, and that's how we come up with Q2. But if you look at it closely, this isn't a strict 100%, and these are not strict 0%. So this is a 5%, 2%, 3%. So the most natural way to apply the softmax in order to preserve exploration in the algorithm is to use these exact probabilities as how often we're going to be taking that action. So these probabilities actually represent the distribution of these actions that we're taking. So basically, softmax makes it very easy for us to come up with a way to combine exploitation and exploration. So the best action will always have the highest probability because it has the highest Q value, and therefore here we're going to use these as our distribution, and we're going to say, okay, we're going to be taking Q2 90% of the time. But 5% of the time, we're still going to be taking Q1, and 2% of the time, we're going to take Q3, and 3% of the time, we're going to be taking Q4. And the beauty here is also that as these values update, as the agent goes through the network more and more and more, it becomes more familiar with the environment, and therefore these updates. So this value, for instance, might become like it might ascertain that this value is actually less or this actually is higher, and so these probabilities will also change as an agent goes through. So even though here we've got Q2, nobody is to say that sometimes 5% of the time, to be more precise, we'll be selecting Q1 as the action to take. And sometimes, or action 1 will be taking action 1. Sometimes we'll be taking action 3, 2% of the time, and action 4 will be taking about 3% of the time. So every action has a chance to play in this process as long as we have enough iterations and the agent goes through lots and lots of times through these states that they're in, and that's how any kind of deep learning algorithm works, that you want to do this many, many, many times so that you learn from experience. And therefore, as you can see here, it's a very natural transition to, we're not just randomly, like an epsilon greedy algorithm, we're not just randomly selecting the actions, we're selecting them based on their softmax values, which makes it like has some logic behind it, not just at random. 10% of the time we're selecting a random action, but there's some logic behind how we're doing it and based on the Q values that we've explored. And so that's the action selection policy that we're going to be using in this course. You're welcome to definitely check out the epsilon greedy action selection policy if you like, but we're going to be predominantly using the softmax action selection policy. And I've got an interesting reading for you. So this is called Adaptive Epsilon Greedy Exploration in Reinforcement Learning Based on Value Differences. It's a 2010 article, and it's interesting because Mike Michel, I'm not sure how to pronounce it, Michael Tokic introduces a different type of algorithm, so an adjusted epsilon greedy algorithm, and called the VDBE algorithm. or epsilon greedy VDB algorithm. You can see it over here, and he actually compares it to the epsilon greedy and softmax, and it's an epsilon greedy algorithm, which basically the main idea behind it is to adjust the value of epsilon depending on the state the agent is in. So if the agent is very certain about the state they're in, then epsilon should be smaller, so there should be less exploration. If the agent is uncertain, epsilon should be higher, should be more exploration. So it is a 2010 article. I'm not sure if this new proposed algorithm is widely used or has been accepted in the community, or if artificial intelligence has moved kind of away from this suggestion. But nevertheless, it will definitely help you reinforce your knowledge about action selection policies, which we discussed. The epsilon greedy and the softmax will help you. It'll give you an opportunity to compare them side by side and also see in which direction people actually think when they want to improve artificial intelligence. So if you're ever planning on creating really interesting algorithms that are pushing the edge of artificial intelligence and pushing the envelope in this space, then this could be a good way for you to see in which direction people think sometimes when they're trying to improve the norms of artificial intelligence, or the norms that existed back then in 2010. So there we go. Hopefully you enjoyed today's tutorial about the action selection policies. We learned about epsilon greedy, epsilon soft, and the softmax. And now you're even more prepared for the practical side of things. And on that note, I look forward to seeing you next time. And until then, enjoy AI.